Hi, I'm Sanjit Seshia, a professor at UC Berkeley. At the outset, I would like to thank the award committee for this honor and the broader community for your interest in and the follow-up research to our work that has enhanced its impact. In this presentation, we will begin by first looking back at our work, then at the results obtained in the decades since, and finally to the exciting future directions that remain to be explored. So looking back, our ICSE 10 paper made three major contributions: Oracle-guided learning, component-based synthesis, and certain novel applications of synthesis. It was also one of the first works to explore the connections between the new wave of program synthesis and the field of machine learning. So let's look at these three contributions in more depth. The idea of Oracle-guided learning in this paper was to formulate synthesis as a dialogue between a learner and oracles, where the oracles can answer two types of queries: an input-output query that, given an input, produces the corresponding output, and a distinguishing input query that produces inputs that differentiate a candidate program from other consistent programs. The paper also made a link to machine learning, more specifically to machine teaching. The second contribution was to think of synthesis as assembling programs from components. For loop-free programs, the components were operators, and there was an efficient encoding to bit vector SMT solving. The third contribution was to introduce new applications of synthesis, such as synthesizing bit hacking tricks and simpler versions of obfuscated malware. In fact, the idea to use a distinguishing input query arose because we realized that standard verification queries were too expensive for some of these applications. So how did these ideas come together? From my own personal perspective, the journey began more than 20 years ago when, as a fresh PhD student at CMU, I was interested in both machine learning and formal methods. And while my PhD thesis on the Euclid SMT solver and verifier explored this a little bit, I started pursuing this connection between the two fields in earnest when I joined the faculty at UC Berkeley, and it was the theme of my NSF career project. Concurrently, I started working on program synthesis with Raz Bodik, then a colleague at Berkeley, and Armando Sola Lezama, who was then a student. And we developed the technique now called counterexample guided inductive synthesis, or CGIS. Around the same time, Sushmit Jha started his PhD at Berkeley under my supervision, and we worked on several topics, including SMT solving for bit vector arithmetic, program synthesis, and in collaboration with Somesh Jha on malware detection. It was in this context that Sushmit started a summer internship at SRI in 2009, seeking to work on exist-for-all SMT solving and on synthesis. It turned out to be a fruitful summer collaboration that led to the writing of our ICSE 10 paper. So now let me look at the decades since we wrote that paper. And I would like to point out that one of the most exciting trends has been the confluence of formal methods, program synthesis, and machine learning. From my personal viewpoint in 2009, I had two epiphanies. First, I realized that many tasks in formal methods, including specification and verification by, for example, proofs by induction, compositional reasoning, abstraction, and so on, all reduce to synthesis problems. Second, I realized that the ICSE 10 work, CGIS, and other projects were all instances of a more general approach to synthesis, one that combines inductive learning, deductive reasoning, and a hypothesis about the structure of the artifact being synthesized, which we now term as syntax guidance. We term this approach as SciDuction, or more concisely as SID, and we wrote a string of papers on this, starting in 2011, 2012 with a DAC 2012 paper and Sushmit's thesis, and then following up with a more detailed article in the Proceedings of IEEE. In the years since, especially in projects such as Escape, TerraSwarm, and VCal, these ideas have been demonstrated in a range of application domains, including software and hardware verification, education, cyber-physical systems, robotics, including human robot systems, and machine learning. This approach to formal verification is now also implemented in a new toolkit called Euclid 5, which is an effort that has been co-led by my former postdoc, Pramod Subramanian. In particular, we've been interested in understanding the theoretical connections between machine learning and program synthesis. A key result appeared in our 2017 Acta Informatica paper, which has three major results. First, it establishes the theoretical framework of oracle-guided inductive synthesis, of which CGIS and our ICSE 10 work are both special cases. In contrast with models that are commonly used in the machine learning literature, such as active learning or query-based learning, in oracle-guided synthesis, one is allowed to design both the learner and the oracle given an so-called oracle interface, which defines the communication between the two. Our second result uses this framework to characterize the relative power of different variants of the CGIS approach. The third result shows how the notion of teaching dimension introduced in machine learning theory can help characterize the complexity of certain oracle-guided synthesis methods. Taken together, these form an initial theoretical framework for formal inductive synthesis, which now other researchers are starting to build upon.